So what I want to do today is this evening I thought we'd just do a quick session, and I'd cover some of the bits of AGK that I haven't actually covered to answer some of the questions, and also there's some bits that aren't in the book as well. So there's the first thing I thought I'd cover was double pole electrical systems. Now, this isn't in the book, and there are questions on it. Now, the way generally aircraft electrical systems work is that you have a metallic airframe, an aluminium airframe with aluminium wings and aluminium thing and an aluminium spar that runs across from one side of the wing to the other side of the wing. And everything is connected by just one wire. So, for example, the battery positive typically goes to the, where does it go? Where does the battery positive wire normally finish up going? Go and shout it out, guys, before I draw too much in and it becomes too obvious.
Alternator.
It's good. You only had a 50-50 chance from my diagram. Try the other thing that's a circular object that sits in the engine compartment.
Starter motor.
Yeah, that's it. So it goes to the starter motor. And this isn't just aeroplanes. I mean, this is the same with your car and everything. Generally, the big wire from the battery goes to the starter motor solenoid coil. And because this is where this is the big current path, isn't it? And then you've got typically you sometimes have a wire from here, or you'll have which is usual, or you'll have a smaller wire from here that will go to the rest of the plane, and the negative side of the battery just connects to the aircraft earth, to the chassis of the plane. So this will just bolt on into the bit of metal in the engine compartment. So in the engine compartment, you probably have a frame, supporting the engine like this, and then this will connect to the bulkhead of the plane, and then there'll be sort of like strengtheners here and things, and this will just connect to somewhere and just like be bolted onto here. And so this will be this is marked like this. So that little symbol means it's the ground. And then if you have a light, for example, one side of the light will then just be connected to the ground, and the other side of the light will then probably have some sort of like it will have a sort of switch in it somewhere, and then that switch will be connected to a fuse somewhere or circuit breaker, and that in turn will probably connect to some sort of bus bar. So that's the circuit. So in other words, everything only has the one wire, because the actual negative side is always connected to ground. And so the plane, if you like, the whole plane's body and the engine frame and everything is the if you like, the negative wire that runs around the system. Now this system doesn't always work for everything. A classic example is, the wingtip strobes that you see on some planes, they go like this. Well, they have a very high voltage discharge lamp in them, and a strobe light it's called, and they have a firing system and a very high voltage capacitive discharge system that makes them go very bright light. Now the trouble is that they produce like they take hundreds and hundreds of amps to fire, but they only take hundreds of amps for like 1,000th of a second when they go and produce those very bright lights. And they can cause a lot of interference to all the electrical systems. So what we tend to do with those is not actually run them through the aircraft's earth. What we do is we actually run a wire from the main buzz bar, obviously to a fuse, to a switch, to the strobe control box that actually makes them wink on each wing. And instead of this being earth, we have another wire. This is the positive wire. The negative wire runs all the way back. And the negative wire will probably connect straight to the battery like that. And the reason why it is because what we don't want to do is we don't want to have this line here that's like 1,000 amps, but for 1,000th of a second, going back through the aircraft's structure, because it will actually interfere with all of the avionics and all the other things. And we call this double pole circuitry. In other words, it's where the negative wire has to be run, and it doesn't use the earth. And wingtip strobes are the classic example of a double pole circuit you find in aircraft. Now the next thing I talk about is compass swinging, because I've seen some questions on compass swinging. Now compass swinging isn't where you, in your fury, you unscrew the compass and attach it to a bit of rope and coil it around your head. What it is that every 3 years the plane has to undergo a sort of certificate of airworthiness, and part of that procedure is where they have to swing the compass, and the compass has to be calibrated. And the way this is done is that the aircraft is taken to a special area of a maintenance department or an airport that's been surveyed to not have electrical cables and things like that and bits and pieces, where the latitude and longitude has been like precisely plotted. Of course, that's not a requirement nowadays because any GPS or your mobile phone can give you that. But basically, there's an area in an airfield that normally has like got a little box that's been drawn on the ground that has compass swing written on it normally, and on this box that says compass swing, you find it's got like on the ground it will have north, south, east, and west. And this has been very accurately surveyed so that it's exactly aligned with true north and south and east and west. And what somebody does is they taxi the plane to this area, and they very, very precisely line the plane up with north, south, east, and west. And then they obviously they have to start the engine, turn all the electrics on that you'd typically be navigating with, make sure their mobile phone's not in their pocket, and you know, all that sort of gear. I mean, the engineer does all of this, and they then write down on a sheet of paper that they all obviously have to sign off and everything. The exact true north and what the compass is reading. So they then produce an error card. Now they can convert from true north to magnetic north. How would you go about that, Rob?
You'd look at what the deviation is at that time when you were doing it, and then apply it.
Is that
Or
correct?
variation.
Variation. And how do you know? And how do you know the difference between variation and deviation? Because you've written down
True to magnetic.
Virgin Bell Company, and you know that variation is the difference between true north and magnetic north. So you can look at the chart, and that will tell you exactly how much variation changes each year. You know the exact time of year, so you can work out the exact variation. That means you can work out the exact magnetic heading the plane was on. That way, you can then, once you've got the difference between magnetic and compass, you can produce the deviation and produce the deviation card. So that's what the compass swing is all about. It's something the engineers do, and they produce the deviation card that sits by the compass. So the next thing I want to talk about is gyro toppling. So what gyro toppling is do you remember we talked about gyros and how you've got the different sorts of gyros. You've got free gyro, you've got sort of earth gyros and you know, free gyros. You've got cage gyros where they can only move in one direction. Well, of course, all gyros, the way they work is they're connected. They don't all make that strange noise. They're connected in your cockpit. So things like on this particular one would be connected to the artificial horizon. This is a free gyro. And what happens is that this remains vertical. And then as the plane moves, like in pitch or banks, then the instrument is reading with the gyro. In other words, the gyro stays still and the plane moves around it. But you can probably imagine that there is kind of a mechanical connection between this and the actual instrument, because obviously the instrument's doing this. This is standing still, and what you see in the cockpit is the horizon moving. But there is a limit, because you can imagine that once the plane moves beyond a certain point, that it can't go round and round and round, because I mean it's connected to compressed air or electrical systems and things and bits. So once it's moved to a certain limit, pitch or roll, it will hit a stop. And once it hits a stop, of course, the gyro is then no longer going to remain a free spinning earth gyro. It will tip because it would hit the stop. And or more accurately, it won't hit the stop. The stop will come round and hit it, causing it to topple. Now, once a gyro's been toppled, of course, you can imagine how gyros work. I mean, they're stable in space, and as soon as you topple it, you know, hit it, it will go boing, doink, and of course, it can't erect itself. So, you know, once the plane then becomes straight and level again, of course, the gyro's still going doing, and it's trying to get itself back. And
That's what we call a toppled gyro. We've done something too extreme in the plane, and we've actually hit the stop on the gyro in the mechanism, whether it's an artificial horizon, a direction indicator, or a turn coordinator. The three gyroscopic instruments all suffer from this. Yeah, there will be a limit as to what you can do in the plane before you topple the gyros. Now, the one that's generally the one that topples them easiest, and the one you get the problems with, is the artificial horizon. So if you do crazy things in an aircraft, aerobatics and things, you will topple the artificial horizon. And once the artificial horizon is toppled, funny enough, it can take an awful long time. I mean, 10, 15 minutes before the damn thing erects itself again. And what happens is you look at in your cockpit, and you look at the artificial horizon, and it sits there going like this. And instead of being a nice straight line, it's going like this. And it's of no use at all. In fact, there is an argument that it can be such a distraction. They say if you've got a toppled artificial horizon, the best thing to do is just to cover it up with a bit of paper, because it's just a distraction, and it causes you as a pilot just to keep looking at it all the time, going. Tyre ply. There's a question on tyre ply. Well, when we talk about the ply of a tyre, you've probably come across this on your cars, particularly if you're into off-roading and things. But the ply is just the number of cords in your tyre. That's all of tyre. When you say, certain sorts of like, particularly when you're talking about cross-ply tyres, you buy certain ply of tyre, which is a measure of strength. So the higher the tyre ply, the more the cords it's got, and that means that the stronger the tyre is. You generally find a lot of aviation tyres are cross-ply tyres, just purely because cross-ply tyres are designed to take load. So radial tyres give you good road holding, and cross-ply tyres are the thing you buy if you want to put tons and tons, or you want to subject the tyre to crashing on the runway all the time, or you've got a truck with you've got a 30-ton truck and you want to stick a tyre on it or something, Right, so the next question, I noticed there was questions on starter warning light. Now, the starter warning light, if you remember, I shouldn't have rubbed that off, should I? I'll put it in. I actually had the circuit diagram on the bloody board, didn't I? So the circuit diagram of the starter motor circuit is this goes to the solenoid, the plus. And then the solenoid sits on top of the starter motor. And then the output from the solenoid goes into the starter motor. The negative of the starter motor is, of course, earth. This is a relay, if you like. And then there's a much thinner wire that goes to the ignition switch and things. Now, what the starter warning light is normally from here. There's a much thinner wire that goes to a cockpit light. Oops.
And this is the starter warning light. So you'll notice that the start circuit for the starter warning light doesn't come from the ignition switch. It actually comes from like the starter motor itself. And a typical starter warning light is in fact on the Cessna is actually this little light here on the top of the cowling. Is the starter warning light. So as part of your checks, it's part of your checks is you make sure the plane remains on the board. Right, so as part of your checks, you want to make sure that the starter warning light goes out. So as soon as you operate the starter and the engine starts, you turn the starter off, starter warning light is out. Now, of course, the problem you've got as a pilot is, yes, it's all very well looking at the starter warning light and going, as soon as the plane starts, you turn ignition off, you go starter warning light out, oil pressure is rising. I mean, all light aircraft checklists, it doesn't matter what you fly, always have starter warning light out, oil pressure is rising. There's the first two things on your starting action checklist. Now, of course, starter warning light out means you must know the starter warning light was on. Because let's face it, it's pointless going starter warning light out if the bulb blew a year ago, isn't it? Because starter warning light will always be out because starter warning light was never on. So on the starter warning light, you can press it. So like, for example, you see this, you see how it's a silver bezel here. Well, if you actually press the light in, you'll find that it's actually got a power to it, and you'll actually make a connection and the light will light up. So you can actually test the low volt light and the starter warning light by just pressing them, yeah, and making them come on manually, just to make sure the light is working and the bulb isn't blown. Or of course you can actually things like your low volt warning light. Of course, when you turn the master switch on, you'll always get low volt warning because of course it will be low volts because the alternator's not running. And of course, when you activate the starter, what a lot of people do is they just activate the starter and have a glance up to make sure the starter warning light is on, so that when they turn the ignition off, starter warning light goes off. Now, going back to our circuit, and this happened to one of our club planes actually. A classic problem with old Cessnas and Pipers in particular is that they have really crappy ignition locks, and they get to a point where you can put the key in upside down and it still works. You can put anything in, screwdriver, hair clip, doesn't matter what you put in the ignition lock, it's still gonna operate the plane. And it doesn't really matter anyway, because all Pipers and Cessnas got the same ignition key anyway, generally. So, I don't think Pipers they've ever had two different ignition keys. All Cessnas, they're all the same key. So, yeah, it's not like a high security lock that they've got on the plane.
which means you can sometimes you can put the key in upside down and you can operate the starter. But of course, it's not when you release the key, it doesn't always turn off because the key is in upside down. And so the starter stays engaged. So the engine starts, and the plane's running, but the starter, the solenoid and the starter are still engaged. So on the end of the starter, you've got a spring, the Bendix spring, and then you've then got a cog. Looks like this. So this cog here is engaged with the teeth of the flywheel that's sitting on the end of the engine, and it's geared. So it's got this is a great big flywheel, and this is a tiny little cog here. So what happens is that the starter remains engaged on the flywheel, which means that as the engine starts, it spins this starter at very high speed. And it's normally disaster if the pilot doesn't spot this straight away, because what happens here is this is a typical 12-volt battery running a 12-volt starter. But if you spin this starter at high speed through the engine, this starter acts as a DC dynamo. And what this starter motor does is it produces electricity. And the amount of electricity it produces is huge. I mean, it'll quite often produce, like on a 12 volts, it'll produce like maybe 30 volts, 32 volts, something like that. And it feeds it back through to the 12-volt battery. So suddenly your plane is no longer a 12-volt plane, it's now a 32-volt plane with 12-volt equipment connected to it. So can you imagine what happens if the pilot wasn't actually aware of what's going on here and hadn't realised this is connected and then turned the avionics master switch to on? What would happen, will be?
Probably going to blow all your fuses.
No, probably isn't going to blow all your fuses. It's probably going to do 15 grand to the damage to all your avionics.
I'll blow all the equipment then.
Yeah. What do you think is going to happen to the Will H? What do you think will happen to the alternator control box and the alternator, the battery, the lights, and all the other things you've got connected to the plane?
They'll cut out.
No, they all blow up as well. So what happens is that your alternator control box, alternator burns out, box burns out, all your lights blow. Basically anything that you've been daft enough to turn on, you basically put in the dustbin. And so, not checking starter warning light, it can be, well, you can write the plane off basically. You can do so much damage to the plane that it's not recoverable, and the insurance company won't pay out for an overload due to starter warning light not checked, because that's just pilot negligence, isn't it? Yeah, they won't. Insurance companies don't pay out for stupid claims where pilots didn't follow a checklist. So this is something to be very, very wary of, this starter warning light. Now, having said that, you can actually if it's a plane that you're used to flying all the time, you will, as the captain of the plane, you will know when you've got starter engaged, because as you start the plane, you'll notice a noise coming from the starter motor. Yeah, it'll go, instead of it, as you release the key, you'll hear a little whine coming from the engine compartment. And as a pilot, generally, as soon as you hear something unusual happens, that you abort what you're doing, and then you think about it. You know, you don't you don't kind of like think on the run and think, well, hang about, what's going wrong here? You know, you just instinctively, you know, you apply power on the runway, you start to gather speed, something unusual happens. You don't start forming a subcommittee and a discussion, and you get out your pilot's operating handbook and you get on your mobile phone. As soon as something untoward happens, you just bring the power back, slam on the brakes, taxi back, and think, what the fuck's gone wrong? You know, what have I done wrong? What's gone wrong? And so as soon as you start the plane, as soon as you hear a little whine, then that's probably starter has got stuck on. And that's normally 90% of the time is because the key is in the ignition lock upside down. And as you release the key, you hand off the key, and you thought it's in the it's gone back to both. It hasn't, it's still in the start position, and it hasn't gone flick all the way back. So that's what starter warning lights all about. Right, were there any other AGK questions that came up where you thought, where it wasn't in the book or I didn't cover it? Technical information that you want me to go through. Because what I want to do next is I want to go through principles of flight on some of the other AGK questions where they talked about principles of flight. Is there anything else you want me to cover?
Paul, in the principles of flight one, are you going to cover the primary and secondary effect of the primary controls?
Yes, I will.
There's questions on that.
Yeah, I'm going to cover that in principles of flight. But
Okay.
yes, but is there anything on AGK, on engine theory, carburetor, fuel, genuine AGK stuff you want me to cover? Because I'll push on with principles of flight. I don't think we'll have a break because I don't want to make this isn't going to be a 2-hour session. I just want to really just do a quick session tonight on all the bits that principles of flight. So this will only take me sort of like half an hour, and then I'll cover 10 minutes of exam technique, and that will be the end of tonight. So we haven't got a lot to get through. Right, now, I've got an aeroplane, and I'm not sure I can do this without an aeroplane. Unfortunately, I stood on my aeroplane a few weeks back. I came into my studio one night, and my studio's all got, as you can probably notice, it's got huge amounts of lighting in it. But unfortunately, in my studio, I don't have a little bulb in it. Yeah, I don't have a sort of something where I can just illuminate it. So I can't come into it at night without, about the equivalent of about 1 kilowatt of lighting coming on. So I came in it one evening and I stood on my little model, my lovely little plane, and broke it. So I probably, I'll tell you what, I'll bring up a picture of an aeroplane. So the first thing I want to do is to talk about the axis of an aircraft. So a light aircraft, all aircraft have three axes. So let's just draw it, and I'll bring up so if we just like imagine a light aircraft. So here's the wings, tail, a sort of a stick diagram of a light aircraft. So the aircraft can move around these axes. So each of these axes has got a name. So we call the axis that runs along it, along the body of the plane, this is called the longitudinal axis. In fact, anything in life, the thing that actually runs from front to back, you call the longitudinal axis. The axis that runs through the wings, this is called the lateral axis. And the thing that runs vertically through the plane is called the normal axis. And these three axes, they work through the center of gravity. So you've got the longitudinal axis going from front to back of the plane. If you like, that actually is pitch. So in other words, the longitudinal axis, when it moves up and down, is the pitch of the aircraft. And how do we what flying control alters pitch? How do you make the nose go up or the nose go down? Rob?
Elevator.
Control column.
So the elevators on the tail, and of course that's the control column, isn't it? So to make the longitudinal axis pitch up or pitch down, we use elevators to control pitch. So the lateral axis runs through the wings, it runs through the center of gravity and from one wing to another wing. And of course, if we want to move, the lateral axis is all about roll, isn't it? So lateral axis is roll. And what controls roll? Will H, you're next.
Ailerons.
Yeah, the ailerons on the end of the wings. Yep. So the ailerons, one goes up, one goes down, and the aircraft rolls. So roll is controlled by ailerons. And then the normal axis, so Rob, your turn, is of course is how the plane yaws. And what controls yaw?
Rudder.
The rudder. So basically, we're controlling the plane about these three axes. Yaw, pitch and roll, rudder controlling the yaw, elevator controlling pitch up and down, and wings level, in other words, the roll is controlled with the aileron on the control column. And we call these the primary flight controls. So the rudder, the elevator, and the aileron, these are your primary flight controls. In other words, the primary flight controls are the controls that you need to keep the plane straight and level. They're the controls you need to fly the plane. Now, besides just the primary flight controls, you've also got secondary flight controls. And what secondary flight controls are other control surfaces. I mean, a classic one, things like flaps, is a secondary control. You might have elevator trim tabs. Elevator trim tabs. You might even have here, you might have a rudder trim tab. But all of these other controls are secondary controls. Now, the secondary controls may be able to be adjusted in the cockpit. They might be adjusted externally. So, for example, rudder trim, for example, is where you can you find that some planes you've got to apply slight right-hand rudder pedal throughout the whole flight. So you find that on the rudder, quite often, there's a tiny trim tab on the end of the rudder, and you can move it by hand, or sometimes just bend it. And what you can do is that's actually a movable rudder trim tab. Now, on twin-engined aeroplanes, if you lose an engine, the plane will naturally yaw. It will yaw towards the DUF engine. So you can't fly it for ages and ages with your foot stuck on the rudder pedal to correct yaw. So on all twin-engined aircrafts, you've actually got this rudder trim is actually inside the cockpit. So normally you find that in the cockpit somewhere, normally on the floor of the aircraft, you'll have another control where you can move it left and right, like a bit like a trim wheel that you see on a single engine plane, and you can alter the rudder trim as well. So some of these secondary controls can be controlled from inside the cockpit. Some of them are maybe external. Now, not to be confused with primary and secondary effects. This is primary controls and secondary controls. Now, I want to talk about something that's a lot more complicated, but there are questions in the unreasonable questions in the AGK exam on it, so I'll cover it. And that's what's called the primary and secondary effects. Now, we've talked about what the ailerons do, we've talked about what the elevators do, we talked about what the rudder does. Now, let's think about ailerons for a time being. So everything about flying is about drag, isn't it? About reduction of drag. And, you know, I mean, drag is the thing that is our biggest enemy in flying. You know, it's the thing that stops a Cessna 152 from doing 500 mile an hour, isn't it? And everything is about reducing drag to a minimum. But of course, aircraft are it's not as straightforward as a car, because I mean the drag is produced by things like the wings themselves. So yeah, you could reduce drag by just soaring off the wings, but of course you're not going to get airborne, are you? So everything about aircraft design is a compromise. You want to get the lift, but at the same time you want to reduce the drag, or you're not going to be able to produce lots of lift without producing lots of drag, because you know you've got these great big wings, for example, you're going through the air, and drag is the biggest problem you've got with all aspects of designing a plane. Now, so let's think about the ailerons, shall we? So the ailerons, what's going to happen is as my wings flying along, and I want to bank this way, and I want to roll the aircraft like this. So if I want to roll the aircraft, I want to put this aileron down, don't I? So I want to put this aileron down so that as I'm going through the air, it's going to now cause a roll in the aircraft. But tell me, what's going to happen, do you think, Rob, if I put this aileron down? What's going to happen to drag?
It'll increase on, well, as more of the wings exposed to the oncoming air, it'll increase the drag.
Right, so that means what I want to do is I want to put this aileron down because I want this wing to rise, because I want to turn left. But if I just put this aileron down and increase the drag on the right, what's going to happen to the plane?
Probably yaw the nose to the right.
Going to yaw right, isn't it? Well, that's a fat lot of good. I want to turn left. I don't want to turn right. So, so that's a secondary effect of an aileron. So, in other words, the secondary effect of an aileron might be adverse yaw. We call that adverse yaw. In other words, that an aileron is going to create a turn in the wrong direction. Who thought of designing that for a bloody aileron? So we have to have extra things built into the plane, like you make one aileron go down as the other aileron on the other side goes up. In other words, as this creates a bit of drag this way, this aileron on the other side, as this one goes down, the other one goes up. And so hopefully the drag from that one going down is going to be equal to the drag from the one on the other side going up. So we try to design into the aircraft things that's going to get around the secondary effects of the controls. But you can imagine you can't design everything out. Like, for example, I'll give you another example. Supposing that we want to turn left again, and I put my foot on the left-hand pedal, rudder will obviously the tip end of the rudder will go to the left, and the plane will then yaw to the left. So as I put my foot on the left-hand rudder pedal, the plane will just suddenly like yaw like this. But if I yaw the plane to the left by just putting my foot on the rudder pedal, you could probably see that the wing on the right-hand wing has just swung through the air, and the left-hand wing has just gone backwards. So what's happened is the right-hand wing has accelerated through the air, the left-hand wing has decelerated. So if I take a wing that's producing lift and I make it go faster through the air, then it's going to produce lift, isn't it? It's going to produce more lift. And if I slow a wing down, it's going to produce less lift. So what happens is, if I put my foot on the left-hand rudder pedal and do nothing with any other controls of the plane, as the plane yaws to the left, this wing is going to produce more lift, and it will cause the plane to roll because of the extra lift I've got on the right-hand wing. So this is what they call a secondary effect. In other words, yaw creates roll. So if you want to turn a plane to the left and you just put your foot on the rudder pedal and make the plane yaw, it'll be a bit uncomfortable for your passengers. Don't do this to somebody who's your first time you get your wife or girlfriend in the plane, because she'll probably throw up all over you. But if you just turn left by stuffing your foot on the rudder pedal, the plane will yaw, and then a few seconds later you'll feel the plane will start to bank and it will turn into that into the yaw. Now the same happens if you just start a turn by just rolling on the turn with the ailerons. Then if you just roll the plane, then what's actually going to happen is, if we roll a plane, I just want to draw a diagram of a plane looking at the back of a plane. So you can probably picture what's going on. Is that if you imagine you've got the body of a plane, and you've got the wings like this, and you've got the tail here at the back of the plane, and what's happened is you've got lift that's acting on both the wings. The lift is acting through the centre of gravity. So here you've got lift. And of course, in order to keep the plane straight and level, lift is going to be equal to weight. I mean, if lift wasn't equal to weight, the plane would go up in the air or come down, wouldn't it? So, I mean, lift must be equal to weight. Obviously, if you're climbing or descending, well, then lift isn't equal to weight. So that's happy days, straight and level flight. Right, now I'm going to roll the wings. So let's just draw that same plane again. So we're going to roll the wings, and here's my tail, sort of at the back here. Now, the wings are producing lift. So if I roll the plane, we've got weight acting here. And hopefully it's the same weight that it was in straight and level flight. But the lift force is going to be here, isn't it? So this is the lift. So can you first off, can you see an immediate issue that's going on here? Will be What's our first thing that you notice that with lift and weight?
Will they be unequal?
They're unequal because the lift is now operating at an angle, isn't it?
Yeah.
So the lift force that's acting vertically is now a cosine angle of bank times lift, and which is going to be less than weight. So as soon as this full arrow going up is less than weight, what's going to happen?
You're going to start descending.
We're going to start descending. So you probably in your flying training, when you start a turn, you're going to have to increase a little bit of back pressure, aren't you, to create more lift? And why do you have to create more lift when you're in a turn? Well, the reason you have to create more lift is because some of your lift force is not all your lift force is acting opposing weight. So you've got to increase lift so that this component equals weight. Now, besides this going on, you might also notice another strange thing that's happened in that you've got a component of lift that's opposing weight, but you've also got a component of lift now that's acting in this direction. So you've got your lift now is resolved into an opposing weight and a sideways force. So that means as soon as you roll the wings, you've got a force pulling the plane sideways. Now we call this force, this is the centripetal force. It's called the centripetal force. I'm not going to go into it too much. We do this to death in principles of flight, but this force physically moves the plane sideways, and if it moves the plane sideways, what's happening is that you can imagine that if you took this plane about the centre of gravity and you moved it in that direction to turn left, well, you've got this great big fin sticking up at the back of the plane, haven't you? So if you just move the plane to the left, the plane will yaw to the left, because if you just take the plane and just move it across the sky to the left, it's not going to want to move to the left. It will actually rotate around the normal axis. And it will yaw, because the fin sticking up will stop the tail moving through the air, so it will just yaw to the left. So in other words, roll creates yaw, yaw creates roll, and we call this the secondary effects. And there's a couple of AGK questions about this, like roll creates pitch, roll create, the secondary effect of roll is yaw, the secondary effect of yaw is roll. Now, all I want to cover for now is the information you need from Principles of Flight to pass the AGK exam. And in fact, Principles of Flight is the next technical exam that we'll be covering. But that, I believe, is the only thing you need to know to pass the AGK exam from Principles of Flight. Now, obviously, you know, when we cover Principles of Flight, I spend like 3 hours going through what we've just discussed on the board. And when I talk about lift drag, yeah, we'll spend another 3 hours going through loads of graphs, lift drag ratio graphs, load factors and things like that. And bits and pieces. The arrow that when we were banking, and I was showing the arrow going at an angle, and we had to produce more lift. Well, we call that the load factor of a plane. So in other words, the angle, the bank angle, increases the wing loading and the G-force. And of course, we feel that G-force, don't we? This wing loading, it's a physical thing. Yeah, when you actually roll the wings and the plane starts to turn, you physically feel that G-force, and we call that the load factor. In other words, it's how much everything's been loaded by. You don't need to memorize what they are for AGK. You do for principles of flight, and we'll cover that when we do principles of flight. So the last thing I want to cover, really, unless you've got any more questions on principles of flight. But if not, what I want to do is I just want to cover the next thing, really, which is exam technique, which is the last thing. So exam technique is basically how you pass an exam. So you've obviously got a question paper, and you've got probably 4 or 5 questions on each page, and then you've got your rough sheets of paper here. Now, the secret of passing exams, and I've got quite a lot of experience of exams, because it is something which I like to do as a bit of a hobby, is I regularly get extra qualifications, not in flying, but in all sorts of other weird subjects. But there is a method to it, right? And the method is all about management. It's not about knowledge, it's about management of how you go about doing these things. So the first thing you've got to be is neat and organized. So on your rough working out sheets, number them all. So just put a page number as you do it. Yeah. Page number 1 in the circle, top right-hand corner. The first thing you do when you walk into an exam, before you look at these questions, is you write your formulas on your rough working out sheet. So it doesn't matter what exam you're doing, it will always have sort of scientific formulas. It will have some sort of chemical interaction, some sort of thing. This is where you you write your square 1.22 times square root of h1 over m. All of that sort of bollocks is you write down your formulas. Now for AGK, just write down what EASA is. So just write this down. And for AGK, write True Virgins Make Dull Company. Just put TVMDC and put ANS and UNOS. So this is all the information I think that you need to pass your AGK exam. That diagram, that and that. Now, don't wait until you need that information, because when you start an exam, all your formulas are in your head and they're all clear. what happens is that when you've been bombarded with centigrades and Fahrenheits and all the other things in an exam and the stress is building, you can't always reconstruct these off the top of your head. So start by writing down, just write down TVMDC, ANS, UNOS, and then put your diagram of EASA and put a line. There we go. That's it. Right. So that's taken you 10 seconds. Right. Start working through your questions. Now, when you need to draw a diagram, and there's a few questions where you need to draw diagrams in the AGK, not so much with AGK, but certainly in the NAV exam, you'll probably need to draw a diagram to answer probably virtually every question. Put the question number in your rough working out sheet. So, supposing we need to draw, supposing we've got a question about airspeed indicator, you can't remember about it. Well, and it's question number 3. We'll just write 3, draw your diagram here, and then when you've drawn your diagram, just put a line underneath it, and you now know that everything relating to question 3 is here. And then just carry on. It doesn't matter if you ask the invigilator for another 3 or 4 sheets of paper. It doesn't matter. I mean, just make it organised like this. Don't do your rough working out sheets. You've got a bit here and a bit here and a bit here and a bit on the side here. Draw a line across every single question and put your question number down on every single one. Work your way through the question paper. Any questions that you're not sure about or it's going to take a long time to answer, it doesn't happen in AGK so much, but there's certainly other subjects where it might take you 3, 4, 5 minutes to work out the answer. Obviously those are ones you're going to have to make a list of to come back to. So you just work your way through it. Any question you're not sure about, if you don't know the answer, just leave it blank and move on. Now, the reason why you leave it blank and you move on and you just make a note here that you've got which ones you're going to revisit is because sometimes when a later question will give you a clue to an earlier question. Now, by that, I mean that on AGK, for example, these questions are just picked out by a computer program from a database of like 250 questions. Now, the computer program is a pretty stupid program, really. How do I know that? Well, I know that because obviously I wrote the program, but what it does is it sort of tries to pick out the right mix of topics and things, but it has no concept of how questions interrelate. So you will quite often find that one question that you think, oh shit, I can't remember which is the bloody pitot and which is the static, oh fuck, and instead of racking your brains, move on, because later on the computer's probably picked a question that's worded such that the question itself answers the question that's come previously, or it's given you a massive clue. So, for example, you can't remember the one question. You might be stupid enough to say the airspeed indicator uses the pitot tube, and what other thing is connected to it? And you're thinking, oh shit, what's the bloody name of that foxy thing now? And you can't remember it. And then another question, 10 questions time, says the what would happen to the VSI if the static port got blocked? And you suddenly think, that was it. It was the static port. Yeah, I remember now. Yeah, I remember everything to do with that. No, and then you've got that knowledge to go back and re-answer the question. So anything you're not sure about, you know, just make a note. You've got to go back because you might actually get the prompt that you need to come back and revisit it. Also, the human brain is a bit more. Sometimes, if you're going through an exam, you'll get a bit flustered in terms of time. And but once you know you've got to the end, you then got a bit more time on your hands. Then go back and revisit all these questions. Now, the reason why you draw nice dots, you keep your working outs neat, is that when you start to move beyond subjects like AGK, the way you do it is you take a question and you convert a question to a diagram. So, like, for example, you would draw, and navigation is a classic one. And I'll show you how to do this when we do navigation, is you probably have a diagram that looks like this for a lot of navigation. And you'll write on this sort of like 15, and you'll have 30 here, and you'll have alpha here, and you'll have angle beta here, and things. And you'll be drawing a diagram. So in other words, what you do is you take a question, you draw a diagram. But you don't then relate to the question ever again. So once you convert a question to a diagram, and then you solve the diagram. And then the reason you keep this working out sheet neat is because when you want to then check all your answers when you've finished everything, and you want to go back and use that time to check, is you don't then reread the questions. What you do is you re-solve your diagrams. And then you can then, if you've got more time, you can then go back and check your diagrams against your questions. So in other words, what you might do, for example, is instead of redoing each question one by one, you just go through the questions on your working out sheet, and you just check your diagrams against the question that you've drawn. You don't you don't do all the mathematics again. You just check to make sure you've got the diagram, and you've RTFQ'd at this end. So you get all your diagrams right, and then you then go back, and then if you've still got more time, you would then solve each of your diagrams one by one and recheck them. So this is why a lot of this is all about the organisation of your working out sheet, your questions, how you go about it. And lastly, then, the most important thing with multi-choice papers is there's always a catch you out question. You've got to do your RTFQ bit, because there's always a simple question about, say, EASA will probably have 15 degrees F. It won't have 15 degrees centigrade, and you'll look at it and you'll go, oh yeah, there we go, 15 degrees, that's it, and you'll tick that as the answer. And of course, they caught you out because what they wanted you to do was to go through and convert centigrade to Fahrenheit. You didn't realise that. You didn't notice the F, and you just put down the centigrade. There's a few things like that in the exam papers. That's really all I want to cover now. I think I've covered everything that you need to know. So there is a multi-choice question. multi-choice mock question in the club. So the multi-choice mock paper is purely based on the exams I gave you. I sent email to you. There was how many were there? Six exams, numbered 2 to 7. I didn't number them, but there's 6 exams numbered 2 to 7, and the mock exam is based on random, well, not random, but the questions picked from those. And to try to make it realistic, let me just check. I just make sure I've covered the AGK aspects. I put 2 duff questions. Yeah, I've put 2 duff questions relating to principles of flight, and we have just covered the principles of flight. Yeah, I've covered the answers tonight, so hopefully you'll have all the knowledge you need to pass the mocks. So I think that's probably the end of AGK. If you want me to talk about the mock exam on a Sunday, or if you want me to cover anything on Sunday, I'm quite happy to help and assist you guys and give you as much help as you want if you feel you need a little bit more assistance over the weekend. But that's it. That's the end. That's really the end of AGK.